I had originally arranged to give this talk at the 2020 Polish Geological Congress in June. Unfortunately, due to the coronavirus, I am unable to present this talk at the Congress, so I have decided to put it on YouTube. My talk today asks the question, can we calculate paleogravity? Before we ask that question, perhaps I should explain what paleogravity is. We all know what gravity is. It is that force which holds us down to the ground. Paleogravity just means ancient. So paleogravity is simply the strength of the Earth's surface gravity in the past. It is widely imagined that paleogravity has been the same for hundreds of millions of years. But this raises an interesting question. Is there any scientific method to check this common assumption? At first, it might seem that we would need a time machine to measure paleogravity, but let's explore the possibility further. Measuring surface gravity today is a simple scientific procedure. Only two measurements are required: weight and mass. We can measure the weight of a known mass and then use these values to calculate paleogravity. On Earth, astronauts weigh a given amount. On the Moon, they weigh only 1/6 what they did on Earth, but their mass has stayed the same. We can therefore measure paleogravity with a simple weight-mass formula. If we had a time machine, we could send our astronauts back into the past to measure the weight, and this would enable us to calculate paleogravity. In the absence of a time machine, we could also calculate paleogravity if we could calculate the weight of any mass that we know existed in the past. A prehistoric animal could be used to calculate paleogravity using the weight math method if we could calculate the animal's weight and mass. Let's consider how we might calculate the weight of an animal. Anderson and his team studied the bones of a range of present-day animals and produced a formula to calculate the weight of an animal based on the dimensions of its leg bones. This formula can predict the weight of land-based animals alive today. The line produced by the formula is shown on this graph. We can see it is relatively accurate, with only a few minor variations from the actual measurements. So we can calculate an animal's weight from just the dimensions of its leg bones. Now let's consider how we could calculate mass. The mass of an animal can be calculated by measuring the volume of a scale model and then multiplying that by the relative scale and density of the animal. Paleontologists have produced accurate reconstructions of a large number of prehistoric animals from just their skeletons. These reconstructions allow the mass of the same land-based animal to be calculated from its body volume and tissue density. Paleogravity can therefore be calculated using the weight from the bone strength method and mass from the volume method. The first dinosaur I looked at was Giraffatitan. This dinosaur has only recently been renamed and was known as Brachiosaurus for years. In the picture on the left, you can see me standing in front of the Berlin Giraffatitan. The picture in the middle is from the Jurassic Park film. The very first dinosaur they saw was Giraffatitan. Below that picture, we can see a number of scientific reconstructions. On the right are a number of models I've used for mass estimates. The top one is from a physical model, and the bottom one is a computer model I produced. This paleogravity calculation indicates that gravity was 0.54 g at about 152 million years ago. Now remember that this is a surprising result because the common assumption is that gravity was the same as today's gravity at 1g. The next dinosaur I looked at was Tyrannosaurus rex. There are at least a dozen specimens of T-Rex, and 4 specimens were suitable for paleogravity calculations. The picture on the left-hand side shows me in front of a cast of the Carnegie T-Rex specimen. The middle picture shows a Stan specimen, and the picture on the right shows the Sioux and the Wankel T-Rex specimens. These 4 specimens produced paleogravity estimates of 0.61g, 0.64g, 0.66g and 0.67g around about 67 million years ago. The next dinosaur I decided to look at was Acrocanthosaurus. Although this dinosaur is about the same length as T-Rex, it is a lot less massive because its body is more narrow. Acrocanthosaurus produced a paleogravity estimate of 0.54g at around about 113 million years ago. About 210 million years ago, there were a group of Coelophysis dinosaurs that became trapped on a floodplain. This has provided us with a range of fossils from small to large of Coelophysis. 2 specimens of Coelophysis produced paleogravity estimates of 0.42g and 0.44g at around about 210 million years ago. One recent dinosaur discovery is the dino bird Giraffatitan. The picture on the left was taken at the Dinosaurs of China exhibition in the UK, and it shows the gigantic size of this animal. Giraffatitan gives a paleogravity estimate of 0.61g at 80 million years ago. Ankylosaurus is one of the armored dinosaurs. Some fossils of these armored dinosaurs are quite remarkable. The picture on the left shows a related species that has formed a lifelike dinosaur mummy. We can perhaps see why the Ankylosaurus model dinosaur seems to be so accurate. Ankylosaurus lived around about the same time as T-Rex, so it gives us a useful comparison between a bipedal and a quadrupedal animal. We can see it gives a similar result to the T-Rex. Ankylosaurus produced a paleogravity estimate of 0.69g at 67 million years ago. Another armored dinosaur was Giraffatitan. There are various reconstructions of this animal. Giraffatitan gives a paleogravity estimate of 0.65g at around 76 million years ago. One well-known British dinosaur is Megalosaurus. This particular reconstruction is in Oxford in the UK. The British Museum also supplies scale models of Megalosaurus, which can be used to estimate mass. Megalosaurus produced a paleogravity estimate of 0.551g at around about 167 million years ago. One well-known ancient mammal is Paraceratherium. This giant rhinoceros has been known by at least 3 different names, depending on whether it was discovered by British, Russian or American paleontologists. On the left-hand side is a reconstruction from 1936. The BBC Walking with Beasts reconstructed this as a slightly less massive animal. On the bottom left-hand side, we can see that Donald Prothero has reconstructed the animal with large ears and a trunk on the cover of his recent book. But these modifications don't affect the mass appreciably. Paraceratherium produces paleogravity estimates of 0.73 g, 0.81 g, and 0.85 g at around about 29 million years ago. The common assumption is that paleogravity was much the same as today's gravity. However, the weight-mass method indicates that paleogravity has been slowly increasing towards our present-day surface gravity. I have written up all these paleogravity calculations in a series of articles. You can find them on my website at dinox.org/pub, as shown at the bottom of the graph. Thank you for listening.